welcome to the 16th lecture in the course Optimization and Data Science. In this lecture I want to summarize several things, extensions of the two last lectures that we had on statistics. So I have chosen here the topic optimization and statistic. I will first speak about hypothesis tests, which are based on the confidence intervals that we already had in the last lecture. I will also introduce another kind of estimator, or basically it's another class of estimators, which are called the maximum likelihood estimators. And this leads directly to the topic, to the relation of optimization problems and statistics. So it's a statistic or stochastic interpretation of the least squares cost functions that we had in the regression problem. And at the end, I want to talk a little bit about how we can generate samples with different distributions. So starting with the hypothesis tests, we use here what we had in the last lecture about the confidence interval. So let us assume we have a sample given which has a normal distribution with the parameters mu for the expectation and sigma squared for the variance, or that we can also assume that the sample has this distribution, which in many cases we have this. For example, we have measurements and measurement data, and in measurement data we often assume that we have a normal distribution. And we already had these two estimators for the expectation and for the variance, these two formulas we had. This is just the mean value as an estimator for the expectation and this type of estimator for the variance. We also computed that we can give, or we know the distribution of the deviation of the mean x bar from the true expectation. We know that this is a student t distribution when we additionally have here this scaling factor on the left hand side. So this difference here from the mean value of our sample to the unknown expectation of the normal distribution which is underlying our samples, this difference, if we scale it with this value here, with our estimator of the variance and the number of points that we have in the sample, then we know this has this special distribution. And this was the distribution. It's a symmetric density function, and here you have the distribution function. So what we obtained is, for the confidence intervals, that we can compute now this bounds of an interval, of a symmetric confidence interval, this bound C, minus C on the lower bound and C on the upper bound. We can compute this by inverting the CDF of the student T distribution, the cumulative distribution function, because we know that this interval could be estimated by 2 times this integral over the density. This is the definition of the probability, and here we used that the density is symmetric, as we can see here on the left picture. It's symmetric around 0, and also the definition is that we can also use the CDF, the cumulative distribution function, which is just the integral of the density. So this basically is just the definition of probabilities for continuous random variables. And now we see here that we have, if we want to have that these values here are in this interval with a probability of gamma, then we can compute the bound of, or the 2 bounds of this interval, by inverting this term here. We have to be given a gamma, we have to invert this term here, this function, which is the CDF, because this function we know, but here we have to invert it with respect to C. So given a probability, we can compute, or we can look up in tables, or we can get this from libraries. We can get the bounds of this confidence intervals. So, and the probability or this estimation of this random variable here can be written in different way. Because if we just look at these two inequalities that we have here, we can of course put this factor here on the other side, and we can also add the unknown expectation mu on the other side, so we can have also an estimate for the mean on confidence interval for a mean with a given probability. So we have here three things. It just depends. It's all the same. The probabilities are all the same. And the parameter c is also the same. We get it from inverting here this function. But we can interpret depending on what we want. If we want to have an estimate on our mean value where it will lie with the given probability or the difference to the unknown expectation, we have and also the scaled deviation from the unknown expectation. And using this property or this this computation that we have computed the bounds of this interval by prescribing gamma here, a probability, we can test for example, the hypothesis that the expectation is mu. So if we don't know what the expectation is, we can test, or we have a guess that mu is the expectation, and we can use this. Because given a gamma, we have the c, as said before, and the scaled deviation, if this is really smaller than the c, then we can say the hypothesis is true. And oftentimes here is used a probability gamma of 0.95. And so this is a simple test. We have our values here of the sample. We can compute the mean. We have the estimator for the variance. So we have n, all is known here. And if we have now the hypothesis mu is some value, we can check if this is true with a given probability. Because from the probability we can compute the bounds. And so this is the first test, that we have a guess what might be the expectation. But we can also do the same thing if we have a sample. We can test the hypothesis that the sample xi has the same mean as another sample yi. Maybe we can we say the yi is the true value, or this is a result of a model. That's in fact what we did. We have a model which computes, or it gives some values. The mean of these values is y bar. So we think this is the truth or the original model output. And now we have changed the model a little bit, and we want to see if the difference is if it's big. So if in statistic the mean value of the changed model is the same with a given probability. So then we replace the mu that we here guessed in the first example by some mean value of something which we assume to be the truth. So this is basically just another interpretation what this mu is. And again we have the same thing, and we can say with a probability of 0.95 our new sample has the same mean than the old one. And if some values are outside these regions, we say they are significant. So we have significant differences. And this is the way that we here somehow measure the difference between two samples in a different way, not taking just the difference, the norm of these samples, but we include our estimators for the variance and give some probability when a difference is too big. So it's a little bit extended than just computing differences of mean values. This would be the naive way. I have an old model which I think it's the right one, but I have several evaluation of this model, and I just compute the mean. I can do the same thing for my new model output and then just compare the mean. But this would give me just one number, and the assumptions on the variance of the data is not included. So this is basically the difference. And of course there can be other ways to test hypotheses, but they are all based on the confidence intervals. And this is just an example where we did this. So we computed spatially the mean, so over time, and then for a climate model this can be done for every grid point here in the atmosphere. I can do this and compare. So we had two models, and again it was the same procedure that I just described. We had two models. We had one model which was the original one. We had several runs of these models with slightly different initial values. So we have not just one model output, we have a sample of model outputs. We computed the mean. Then we have the different model with a slightly changed, and we want to see how big is the difference. So and instead of just computing the differences of the mean, we performed this test pointwise in space, and then we can see when the values are bigger than the bounds that the confidence intervals here is giving us, so bigger than this C. And for this 95 or 0.95 probability and the n that we had here, the values were about 2. So all values giving in the absolute value a value bigger than 2, they are significant. So they lie outside of this confidence intervals and these points. Okay, the next topic is a different kind of estimators. We had, in the last lecture I just gave these two estimators for the mean value and the variance, and they were directly based, maybe the mean value on some intuitive usage. How can I estimate an expectation? And the variance was maybe also a little bit intuitive, but we had a different factor in front that ensures that this estimator was unbiased. Maximum likelihood estimators are a more theoretical idea to design or to find estimators for arbitrary parameters. And here's the definition. So again, we have a sample and we want to estimate a parameter of the underlying distribution. This parameter in general is just here called P. It's a real number usually. And then we define the maximum likelihood estimator as the maximum of the likelihood function. And the likelihood function is just defined by multiplying all probabilities of the different sample realizations. So the probability that the sample takes a given value, and so this is here just a real number xi, and this is the probability, depending of course on the underlying parameter p, the probability that the ith sample takes this real number. So we have a function and we multiply all these probabilities for all indices, for all random variables in the sample. So we have a function now on the parameter p and on a vector in Rn, which are the values here that of this probability, so the values that the random variable should take in this probability. So this gives here a product, and this is the case where if the xi are discrete and if we have continuous distribution, then we multiply here the values of the density function of this value xi. So this is the definition. So this is the likelihood of a parameter and a vector of real numbers. So the likelihood that is the probability that the random sample takes these values that are given in the vector x here as a vector of Rn. And there is an additional parameter, input here is the parameter p. And now the maximum likelihood estimator is the parameter value p where this function has the biggest likelihood. So, and again, as an estimator is a random function, is a random variable itself, I insert here also the sample, which in our definition is a random variable, so a vector of random variable. So again, the estimator is a random variable. Yeah, so we can say that the maximum likelihood estimate, so the result that we get for the p, is the value of the parameter p that is most likely for the given sample. Because here we take into account the values of the sample and we maximize with respect to p. This is again a random variable here because we insert here random variables, and the estimate then is the parameter itself if we put here the realizations of the random sample. And to consider two examples, I want to give. The first example is a discrete random variable, and again this is the binomial distribution that we had in the last lecture, which is an example for a repeated random experiment where we have two possible outcomes. So it might be a coin toss, but it might be also another thing where the probability of every try is not just 1/2. So we say we want to find the unknown parameter p, which is the probability for result 1, let's say, in one single try. If we denote the two possible outcomes here just for simplicity by 0 and 1, so like two sides of the coin. So for the coin, for the perfect coin, we would have p equal 1/2, but let's assume we have a not perfect coin and we want to estimate what is the probability that we get a 1 in one try. And the random variable that we consider here is that it's how many times we get the result 1 in n tries. So the random variable takes the value k if we have k times the result 1 in n tries. And the distribution, this is exactly the distribution, is the binomial distribution that we had in the last lecture. And assume we have one realization, so we have n tries, and we have seen now there is a given number k. Then the likelihood function, because we just have one random variable, our random sample consists just of one experiment, so the product here is just taken over one probability, so it's just this one, that we have the probability with the parameter p that x is equal k. If we now perform the maximum likelihood estimate, so we are looking for the maximum here of the likelihood function, and this is this probability, and we can also take the logarithm because we have to compute the maximum of this function, but it's easier to compute the logarithm of this function because we can do this because the logarithm function is monotonic increasing. So if we're maximizing p, we can also maximizing the logarithm of p. And if we do this, here we have again the function that we want to maximize, and we want to do this. This is a function from r to r, because p is a real number between 0 and 1, and we get some, we can compute the maximum of this function, or the maximizer of this function, by using our optimality condition that we already have. So here optimization is just a tool to find the maximum likelihood estimator, because as the name says, there is a maximum involved. And this is one task for you. If you now take a sheet of paper, you can, here you already find that I applied the logarithm, because then I get just the sum, and it's not difficult to compute here the derivative, the first derivative, and then you can apply the first order necessary optimality condition for a maximizer, which is the same as for a minimizer. The derivative has to be 0. So stop the tape, take a sheet of paper and compute this. This is a little exercise. Okay, I hope you did this. It's not very difficult. The first term does not depend on p, and the other one, the derivative of the logarithm, is just 1 over p. Then we can compute, have these two terms, can compute this and get this relation here equal to 0. This has to be, because this is the first order necessary condition, and this gives as a candidate for a minimizer the P star K over N. Okay, and to see that this is really the maximizer, we need the second order optimality condition, which you know already from school. If you have first derivative equal to 0, you have to check the second derivative. So again, this is a small exercise for you. Stop the tape, take a sheet of paper and compute the second derivative. This is a good exercise. Yeah, and we see here, this is the second derivative. And you can see here that for all p in 0, 1, here we have positive terms, here we have also positive term, and here we have negative one. So the second derivative is less than 0, which is the necessary, and it's a sufficient, that's important, a sufficient optimality condition for a maximizer. So P star K over N is the maximizer, and this is what we intuitively would have guessed. If we have performed N tries and we find K, have K successes, or K times the value 1, then we would say an estimator is that in every try the probability is K divided by N, but we have only one experiment. But this is the maximum likelihood estimator. For a continuous random variable, it's a little bit, might be more difficult, because now we have to maximize a function. So let us take, we know that we have a sample which is normally distributed, but we don't know the expectation. So it's a little bit similar to the example with the test in the beginning of this lecture. And we can write down the likelihood function, which looks like this. Now here for general, for n tries. And the norm, I put here the density for the normal distribution with variance sigma squared and mean mu, or expectation mu to be precise. And then if we now take the rules for the exponential function, that a product of exponential gives the sum in the exponent, then we get here this relation, and we also get a multiplication here of all this factor, which gives this factor here. But now we have this exponential here in this term in the exponent of the exponential function. And we also know that the exponential function is strict monotonically growing or increasing. So what we can do is now we can, of course, in the first place, we can omit this factor, because here's no mu inside. We want to maximize with respect to mu. This is just a factor, so we can skip this factor. And since the exponential function is monotonically growing, we can also compute the maximizer just of the exponent here. So we get here, and since we have here a negative sign, we can take the minimizer of just this sum, because this again is a constant factor, constant because we are only interested in the mu. So what we now have to do, we have to minimize this quadratic sum here, or sum of quadratic terms. And if we call this again just a function phi of mu, we want to compute now the minimizer of this function. And this is again just a function of one variable with values in R. We can just compute the derivative, which is easy. Z is equal to 0, and obtain that we get here mu is like this. So this is the minimizer of this function, because we have also the second derivative of this function. So here again another one, another time computing the derivative, we get a constant value as in the last example, which is greater than 0. So this is really a minimizer of this function. So, and this is again the mean. So the mean is the maximum likelihood estimator for the expectation of normally distributed random samples, independent from the variance. So this is another way to come to the mean as an estimator for the expectation. This would be an idea. So the maximum likelihood method is a way to construct estimators. We have done it here only for very simple ones where this construction was not necessary. We already saw that the mean is an intuitive way to estimate an expectation, not only for normal distributed random samples. And in the last example, as I said, also taking k over n is also an intuitive estimate for the probability that there is success in one try of this coin toss or whatever this experiment might be. But this derivation of the maximum likelihood estimator for continuous random variables which are normally distributed directly leads to the interpretation of our least squares cost functions that we had in the regression problem. Because remember, we had this example here, we had the linear regression where we just wanted to find here the best fit and minimize the distance between the points and the function. We had a sum of non-negative values, and this we can say we minimize just one sum or all terms in the sum. So one of this quadratic term here, we minimize this. We can look how this can be interpreted, because minimizing the sum of quadratics means we have to minimize every term in the sum. So if we look at this, we can do now the other way around. In the last section, I was coming from the density of the a normal distributed random variable. Now I'm going the other way around. I can interpret this difference of this quadratic difference of these two terms. I can write it like this and just include some arbitrary value here, which is then later interpreted as a variance, but it's just a positive number. The minimum, it's the same task, minimizing this function, then minimizing this function, if I'm just interested in x. Of course, the value here of this term changes, but if I'm just interested in the x, there's no difference. So this is equivalent in this sense. And again, if I change the sign here, come to the maximum. If I use the exponential, I can also come to the maximum of this exponential, and I can also put this additional factor here inside. So these problems are equivalent in the way that if I'm just looking for the x. And this, at the end, is again the density of the normal distribution with variance sigma squared. So the minimizer of one term in the sum is the maximum likelihood estimate for the model parameter x here. If the difference of the model and the data is considered as a random variable, or one of the two, it makes sense to consider the data as a random variable, and for example my model output here as given, but it might be also the other way around, that my model has some stochastic behavior. So basically this doesn't matter here, it just matters how I interpret the sigma, and in many cases I will interpret the data as a random variable, and the sigma, for example, the standard deviation of the measurements. And if I can do this in one sum, I can do it also in one term of the sum, one quadratic term of the sum. I can do it also for the whole sum. Now it's getting here with the number of points that I had was m, but this gives again the same computation that we had. And this is the density of the multivariate normal distribution with common variances sigma squared now. If I assume that all my data, for example, or all difference have the same variance, so the interpretation is the data considered as a random variable with the expectation zk, lowercase zk, then means find the parameter such the model output fits the expectation of the data, and it's the maximum likelihood estimator. This can be easily generalized because the standard least squares cost function was looking like this. We had already included the variances in the interpretation, but of course I can also use different variances for different data. So I have sigma case here in the squared. This then gives the weighted least squares function, where we have then here the inverse of the diagonal matrix, and the diagonal matrix just includes the variances on the diagonal. And we can also include covariances and the covariance matrix, and these leads to the generalized least squares function, where we have the same term here, but we have the inverse of the covariance matrix inside. The last point I want to make in this lecture is the generation of that I want to treat in this lecture is the generation of samples. So we already saw how we can generate uniform distributed samples, because we have nearly every programming language we have implemented these pseudo-random generators that we had in lecture 14. And there is an easy algorithm, easy to evaluate, or to evaluate this function here, an easy algorithm that generates normal distributed random numbers. The derivation is not that easy, because we have to take into account then integral transformations. So the derivation of this formula is not that easy, but we omit this here. But usually you will find also functions in programming languages that directly generate standard normal distributed random vectors, or also normal distributed random vectors with a prescribed expectation and variance. But this is the basic idea is connected to this algorithm here, where if two uniform distributed random vectors are given, the function generates two standard normal distributed random vectors by simple applying logarithm and cosine and sine functions. It's more interesting to how to generate now for a given arbitrary distribution. Here it's always the example with the chi-squared. So I want to generate a random sample for arbitrary CDF that I have, the capital Fx. And what I have is a uniform distributed sample, which I can get easily from a pseudo-random number generator. And what I have to do is then somehow again to invert the CDF function capital F, because if I generate here a random sample, uniform random sample, these are 50 sample points here, then I just have to somehow project this on the CDF and then take the corresponding points on the x-axis of the CDF. So this is the basic principle of a random sampling, or what's also called Monte-Carlo sample, which is easy from the idea, but of course it includes the inversion of the CDF, but this can also be found in library function or in functions or in tables. But what you can also see here, if I have an interval, or I have to do this for the interval 0, 1 of probabilities here, and if I use a uniform sample, it might be that it's not that uniform as I would assume, because I have here 50 points you can see, and just taking 50 random numbers in the interval 0, 1 with uniform distribution, I still have here some gaps, and I have here some what's called a cluster or accumulation of values. And this, of course, also influences the values that I get here. So it's clear that in these regions here, where the CDF is very steep, so it grows rapidly, that I get many values here, but I also have here, where I have these gaps, I generate here also big gaps in the generated random variables now of the chi-squared distribution. But this is the basic idea, and this I can do for any CDF that I have, but I need the inverted CDF, which can be defined like this here. So it's not a complete inversion of the function. So it's not f to the power of -1. I'm just looking for the corresponding values here which satisfy this relation. So in fact I do here from this random variables in geometry, I would say I take the projection onto the curve and then going to the argument of the CDF. Another way, or a better way to do this, to avoid these clusters that we could see here we have a clustering, and 50 points are not that few. So if I take even less points, you can see it here, even just 20 points, you also have a clustering somehow here, and here there are some gaps. This is just the standard sampling, and the idea of the stratified sampling is that I subdivide the interval 0, 1 of the probability into subintervals. Here these were 10, and then I just take 2 random points in the subintervals, and this, also with 20 points now leads to a more uniformly here distributed values in 0, 1. Again, I have to do the same thing, invert the density, the CDF here, the cumulative distribution function, and I get points here now, which look a little bit better than this one. So this is the idea of the stratified sample. For higher dimensions is what's called Latin hypercube samples. So it's a generalization of the stratified sampling in higher dimensions, so dimension n. And here's an example for dimension 2. So what I do now, if we go back to the stratified sample, I always started with generating numbers in 0, 1, so in the range of the probabilities, and I take uniform distributed values here and then projected them on the CDF, and then computed the arguments of the CDF. And so I do the same thing now, but if I have now more dimensions, I do it in every dimension. I split up the interval 0, 1 into subintervals. This would be the same as in the stratified sample. That's what I also did here. Here I split it up in 10 subintervals in this one dimension and computed a random number in every of these subintervals of 0, 1. Now I have more dimensions, so I do the same thing. I choose in every of my dimension, I split the interval 0, 1 into m equidistant subintervals. But now I have different dimensions, so what I now do, I compute for every dimension a permutation of the subinterval. So in my example here, this is the first permutation for this dimension. This is another permutation for the other dimension, but it could be also the same. And then what I do is I take the first permutation here. The first value is 2, and the first one in the second dimension is 4. So I take now at the first point, I put in the second interval in this dimension and the fourth in this dimension. So it gives me this box here in 2 dimensions, where I now put my first random point inside this box. This is described by this formula. And if I have another dimension, I would compute a third permutation, or I would choose a third permutation, and this would give me the box in the third direction. So this is the idea, and what is happening then, that I get this distribution where on there is in no row in this 2-dimensional setting, in no row there is a second point here, and in no column there are 2 points. There's also no second point in a column. This is what this method gives. So this is an extension of the stratified sample for higher dimensions, and it can be proven that the Latin hypercube samples have a better convergence properties, which means if I want to estimate parameters, I need in the convergence less dimensions or less evaluations of the random variable. So the number n was this in our definition of the estimators, that I need to have convergence of the estimator is smaller. So they have a better quality. Of course, in reality, I never get into these high numbers of evaluations that I really use this asymptotic behavior, but Latin hypercube samples are regarded the best ones that one can take in higher dimension, and it's not that easy to compute them. There are also in libraries you can find functions that automatically generate Latin hypercube samples. Okay, and that's it for this lecture. So we had confidence intervals already in the last lecture. They can be used to test hypotheses, and this is based on the assumption that the data are normally distributed. And the hypothesis test can be seen as a different way to measure difference between data sets, because it takes into account the variance of the data. We need the inverse CDF, but we can get them from libraries or tables. And our least squares cost functions can be interpreted as a special kind of estimate, the maximum likelihood estimator. And at the end, stratified and Latin hypercube sample are important ways to generate samples. And of course, we need again the inverse CDF to generate samples for non-uniform probability distribution.